Let's take a look at some zone valve wiring. And specifically, we're going to take a look at some of the ways that some of the zone valves are wired in a hydronic system, whether it's a 2, a 3, or a 4-wire zone valve type of a system. So the first thing that we'll hit up on here is this particular handout that I have is one that I pulled some of the pictures out of our modern hydronic heating textbook that you guys have reference to as one of your textbooks. A basic 24-volt 2-valve system. What we're going to take a look at is in figure 9-60 in here. What we're showing is a simple diagram showing a 24-volt transformer, 120 to 24-volt transformer. We're showing a basic standard thermostat going to a 24-volt internal motor of some sort in our application. So this particular zone valve motor in a majority of these systems, not that it matters, but a lot of the manufacturers use what they call a synchronous motor. And now it's a motor that essentially you're not pulling power off. It never really, there might be a slight, very slight increase in power consumption while it's opening, but not a significant amount more. There are other ones that will do that as well. But no matter what the zone valve is that you're using, you absolutely must take a look at the power consumption of that. So bottom line is we're looking at 24 volts going in from a thermostat directly into the zone valve actuator motor. Now, as a technician, you're going to want to definitely be looking at finding the motor, looking at a diagram to identify what those leads are. Now, a simple 2-valve system, you're only going to have 2 wires, so it doesn't matter which one you hook up first or second or common or hot, anything like that. That's typically what we do. And then of course, that lead there is going to be the 24 volts AC common. So that's what that one is going to be. And then obviously that goes back. You may or may not have it where it's possible that this secondary side could be grounded. That's a possibility. It sure makes for troubleshooting a little bit easier, but that's essentially what a basic system would be. Now, power consumption, let's talk a little bit about that. The VA power consumption of the zone valve typically is always going to be listed. You want to find out that power consumption or how many VA. Look at the manufacturer's literature to find out what that is. So power consumption. So look at the literature. Find out how many VA that it is. So whatever the number of VA, you're going to have to identify that. So X amount of zone valves, you're going to have to multiply if you got 5 zone valves or 6 or whatever it might be. Now make sure that you have a transformer, a power supply system that is sized big enough to handle those zone valves. So there's a good little rule of thumb that your textbook had identified in there as well. And that one is basically to add all the VA ratings of all the zone valves. So we're talking about the power consumption of the zone valves, of the motors, and then what you're going to do that would be in that circuit. Now that may also include thermostats as well. So you want to be, if the thermostat has a power consumption, make sure you do that. Now the one that I'm showing you here does not require a common, so it's not an electronic one, but many of the electronic ones do have some sort of a power consumption. Now, then what you're going to do is once you figure out the power consumption of all your consuming devices, you're going to want to add approximately about maybe 10 to 15 VA more than that total. And that gives you a little bit of a cushion in case some of the motors pull a little bit more or a little bit, just a little bit more consumption. So that's essentially what is going on. So for me as a tech, what I'm looking for specifically is I look for which one of these is the hot. That's what I want to find out. Which one of these is my common. I typically will ohm those out. So the resistance between these two are going to identify that as a certain amount of resistance, and I don't know exactly what it's going to be. I just know that it's not going to be 0 and it's not going to be infinite. It'll be something that's in between there, but that's typically what you identify. So let's take a look at the rest of these particular 2, 3, and 4 wire valves, and what are the differences and how do we simplify these. So in figure 9-61 in your textbook, they identify essentially what we call what is a 2-wire zone valve. Now, it doesn't matter if this is done residentially or commercially. Your typical two-wire zone valve is going to have a motor of some sort. It's going to have a hot lead and it's going to have a common lead, and it'll have some apparent resistance, but that's all there is. So a lot of our commercial hydronic systems, they will a lot of times not require any type of a feedback or an end switch of some sort. They don't require that because the zone valve, they will know that based on their sensors that might be installed in the system that hot water is available all the time. They're not turning on and off a boiler based on a demand. That hot water is always available, so that's why that would be the case there. So here's a simple 2-wire zone valve. Now a 3-wire zone valve is one that there are some out there, and it is one that on the 3-wire, what they do is they simply take the hot lead that would be identified in a motor. They'll identify some sort of a lead. Now it could be the hot, it could be the common. There is nothing that says it has to be the hot. And what they do is internally, they will have a jumper that goes directly and feeds the end switch up to here. Now the function of this end switch is such that when I give a T-stat demand into that device and I feed this loop, what it does is it sends 24 volts power into the motor, assuming there's a complete path. This would of course go to my common. Then the next thing that it does is that when this zone valve opens completely. Now I'm making an assumption that this is a typical normally closed zone valve. They do not have to be. They could be normally closed, they could be normally open. You have to figure out what is available, normally closed or normally open. So what happens now in this is that when you power up that zone valve actuator, that is going to drive that actuator completely the opposite of the normal position. So if it is a normally closed, it will drive that valve open. When it goes to the complete opposite of the, let's call it the non-failsafe type mode in this case, so if that valve opens up, that's when this particular switch will now close. So this right here, that little end switch, is going to close when the valve drives, let's call it fully. Now what that means, simply the opposite. It's either going to drive it open or it'll drive it closed. It depends on the system. Now typically the most common would be that would drive it open, and residentially absolutely and most likely most of these systems are going to typically be the default of normally closed. Whoops, excuse me. They will typically be, they will typically be normally closed, and then you drive them open when you energize them is typically how that happens. Now on the 4-wire valve, this is actually what I would consider as the preferred zone valve application, and I think in a lot of ways it makes the job much easier. It allows you to have an isolated end switch that is completely separate from the power supply system that drives the motor of the actual damper, or of the zone valve. So what this allows me to do is when the thermostat drives this valve open, so once I energize that valve, so let's say you might have a separate 24 volts AC as an example, power supply as an example. What they will do then is that power supply will drive that valve 100% to its opposite position. So normally closed valves go open. Once the valve drives to that fully open position, you can then take that end switch, those terminals or those wires, and they typically will then go, they would oftentimes go to, let's say, an Aquastat they would go to the Aquastat demand terminals. So is what they would do, Aquastat demand terminals. So when they do that, so what would typically happen then is if, let's just say, for example, if you were to look at a typical zone valve application with an Aquastat, you would have essentially maybe like this could become terminal T, and when that valve closes, then, or this end switch closes, that would also go to the other terminal T. Or it's going to be the demand, let's call it heat demand terminals. And that's simply how that typically will end up working on there. So essentially the 2, 3, and 4 wire system, the big thing is they all have the same type of a motor that's going to drive that. The voltage could be 20, the voltage could be 120, the voltage could be 24 volts AC, they could be 240 volts AC. It's not super common residentially, but commercially, your apartment buildings, you guys might run into 120 volt type valves. It depends on the application of what it is. This is by far residentially, this is normal for a residential type of a system. So 2, 3, and 4 wire. All right, so let's take a look at a system and what does it look like when we power this up. So I have the first system is a basic 3-wire system that we're going to connect to an Aquastat type relay, 24 volt zone valves, and we have multiples of these zone valves. Now, a couple of things I want to point out in here. The diagram on the left, what we're doing is we have, for whatever reason, this Aquastat has allowed us to use the power supply system from the transformer that's into the Aquastat. So this one we're going to deem as the common in this case. And what they're doing then is they're pulling from the one side of the transformer is what they're doing. I'm going to get the highlighter out. They're going to pull it from that side, from terminal T. They're going to feed the first thermostat. They're going to feed all of the thermostats with that same power consumption or that power wire. And of course, all of these thermostats are going to be fed from the same power supply. Now, of course, you absolutely have to look at what is the rating. You have to look at the rules. What is the VA rating of that transformer? So you better know what that VA consumption is allowed. You know, what are you going to allow? So you got to know that. That's a big if. So sometimes it's maybe 2 zone valves you can do. There's some that might be 3 zone valves. But you may, this is just one possibility. I would probably recommend against using this one if you have, if there's any way that you can use an external one, and I'm going to show you that next. But this is one way. So the bottom line is we're going to take 24 volts input to all of these. So that's 24 volts, 24 to every one of these. Upon a demand, we're going to then complete the circuit through the thermostat. We're going to power up that zone valve actuator. Now this simply just goes right back to the common. So this one is going to go back to the common, which is going to be tied on that transformer. So now my zone valve is actually driving 100% to the opposite, or normally the open position in this case. Now that being said, that means now we're going to take power and send it through. This switch will now go to its closed position. So now we're going to drive this, we're going to send that power, that 24 volts power through the thermostat, and we're going to send that power to complete the T to T circuit, which would, of course, what it's going to do is it's going to allow us to energize this relay coil that's right there. That's part of that Aquastat. So that's what it's going to do. Now, any one of these, what I want to point out to you is that every single one of these thermostats, the end switch, this end switch here to here to here, they are completely in parallel between the T and the T terminals. That is this right here, the T and T terminals that are right there, these 2 terminals, that is what you have to identify in your boiler system. This is going to be what we identify as the heat demand terminal. Now, in some cases, some boiler systems, they will have multiples of those depending on the control system. If it's a more advanced boiler, they might have 2, 3, 4 of those. If it's a lower demand one, like these Aquastat type systems, they're just going to have one heat demand terminal as a general rule. And you'll notice every one of these, you're going to have the same thing. So in other words, T is going to feed every one of these and every one of these systems. And then essentially what we're going to do is feed when the end switch closes. If any one of these end switches, so if this is, let's say this is 4, 3, 2, and 1, if any one of those 4 close, it will then be all of those end switches are essentially wired in parallel. If any one of those closes, that would then take care of the TNT contact closure, which of course provides a heating demand. And then at that point, of course, that would then close the relay contact. That allows your burner circuit, your circulator circuit to function, assuming the Aquastat has as the boiler is sensing that hey, we need to operate. So this is essentially how a typical 3-wire zone valve system would work. The big thing that is critical here to recognize is all of these are in parallel. 1, 2, 3, and 4 are all wired in parallel. That's one big thing. And all of the motors on all of these, they are also wired in parallel. So but they're of course wired in series with the individual thermostats. So if any one of the thermostats closes and has a demand, that will then send power just to that one zone valve, but it does complete the circuit, and that's typically how that would be done. Now, I'm gonna move on over into the one on the far right here. And the one on the far right, fellas, what it's doing here, it is using a separate 24-volt isolation transformer. Now, you might be saying, well, why would we want to use that external transformer that we're showing you here, and then we're using an isolation relay in addition to that? That just seems like a lot of extra work to do in here. But one of the problems that we run into in a typical, especially in 3-wire systems, but one of the problems we run into is that if we don't want to have it where this transformer that's here, I don't want that transformer and this transformer to be fighting each other. And that is indeed a possibility and sometimes it's difficult to parallel those two in certain applications, whether it's due to phasing a transformer or just due to the different available power that is typical of them. So this diagram on the right side is really by far the more typical, the more common way that this would be done. Now, there are, I would say, not a ton of systems out there that are using the 3-wire zone valves, but there are definitely some. I know of a couple of manufacturers that make these 3-wire zone valves. The big thing you got to remember then is you're going to have to be a little bit cautious and careful to not have these transformers fighting each other. So the way this is done is this diagram on the far right is really a very good diagram to totally save and prevent any issues going on into the Aquastat or this transformer. They are completely isolated. Now in this case, everything that I told you earlier falls the same truth. You've got 24 volts hot coming from this particular system. We go through the thermostat, we power up the motor, we send power up to the switch. Once the zone valve gets completely to the opposite position, typically that would be the valve opened. Now let's go ahead and close the switch. We complete that path, and essentially what it does is all of these zone valves, so what happens in this situation, this little set of contacts right there now will complete the circuit to energize the relay coil of the isolation relay. Once if any one of these zone valves, whether it's 1, 2, 3, or 4, if any one of those zone valves closes and that switch closes, that sends 24 volts up to this particular relay or whatever that voltage happens to be. And then, of course, that closes that set of contacts. That completes the circuit for TNT, and the boiler now knows that, hey, there is a demand in the system, and the boiler will do what an Aquastat will typically do, or any heat demand input will do that. So typically that means, hey, we're going to close this set of contacts, we're going to power up the circulator, we're going to now also allow my burner circuit to function, assuming the boiler water temperature is appropriate. And that's normally how this would be. So zone 1, 2, 3, or 4, it makes no difference. Any one of these, they're all wired in parallel as far as the end switch, and they're all wired in series with each individual thermostat for those zones. And that's probably a very, that is a typical way that we will set systems like this up. So that is a 3-wire system. So let's take a look at the 4-wire system. Now, if you remember now, the 4-wire system, we happen to have on this 4-wire system, we happen to have a thermostat that's going to be wired in series with the zone valve actuator. We're going to pull power from the external transformer, which is typical. We are going to feed that all the way directly through to the thermostat, through the thermostat on demand. We power up the actuator, and then we go back to common. So the external transformer is handling all of the power consumption of the thermostats, as an example. It is handling all the zone valves as far as the motors on those zone valves. That's primarily what it's doing. The TNT connection that's on the Aquastat that's powering up the relay coil, that is solely and completely isolated to handle this particular set of contacts. That isolated set of contacts, which would be, of course, providing your heat demand input to that boiler system, is how that's done. So if you go to, I would say, 90-some% of all the basic hydronic systems that are out there in our industry, this is essentially how that will be done. You'll have, if you've got a 2, 3, 4 zone system, you will have zone 1, 2, 3, or 4. Any one of those thermostats has a demand. We power up the zone valve actuators. We close this set of the end switch, and if any one of those end switch is energized or is closed, that will then complete the circuit to the heat demand input for any one of the Aquastat demands. So this right here then ends up being what I'm going to call a heat demand terminal. And you have to find out where that is at. So if it's a basic system, they might have TNT, but you have to figure that out. Usually we can look at something on the control circuit that says how is this demand covered, and you have to know whether is this a demand for domestic water, or is this the demand for heating of the building? What is it going to be? And you have to make sure you go to the appropriate terminals on there. All right. The last thing that I would add on this particular one, on this particular system, again, if I've got this zone, let's say if this zone valve pulls, let's just say that one pulls, let's say 15 VA of power consumption. And if they all pulled 15 VA, I would have to have at least 15 VA per zone, per actuator, times the number of zone valves. So in this case, maybe I have 4. So that would give me roughly 60 VA, okay? And then, of course, you would have to add a little bit of a cushion. So maybe we add another 10 to that. Now that puts me at 70 VA. That is the demand that I need to handle my loads. Now in this particular case, 70 VA, not VAC. 70 VA, okay, so that would be basically like, let's call it a 70 VA transformer. Now you're not going to probably find a 70 VA transformer at 24 volts. So what we would likely have to do is we may have to take the more likely possible way that this would be done is we may end up taking a 40 VA transformer, and so we might do 2 40 VA transformers that we would use, and we can then take those 2 transformers and parallel those transformers, which is a very simple way to do that, as long as you check them out appropriately, make sure they're phased correctly, and you should be in pretty good shape. So that's typically how that would be done. So that was essentially how a 2, a 3, and a 4-wire zone valve system the zone valves themselves actually are wired into a basic system or just simply wired from the thermostats appropriately.